Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name's Ebby, lead tutor for Math and Political Science. In today's video, we will have an introduction to integration with the definition and approximation techniques. Let's get started. In our first example, we will utilize the Riemann Sum approximation and take left endpoints to estimate the area under the curve. The function we want to estimate is f of x equals 1 over x from x equals 1 to x equals 2 using 4 rectangles. Basically, Riemann sums is taking the area of rectangles to estimate the area under the curve. Let's first sketch it. And then we want to find delta x. Delta x is considered the width of each rectangle. And it's always given by the same formula, b minus a divided by n. B is the upper bound, A is the lower bound, and N is the number of rectangles. In this case, it's 2 minus 1 over 4. Now that we have the width of each rectangle, we need to obtain the heights. The heights are going to be different. The heights always depend on which endpoint you're taking, left, right, or even midpoints. Let's first write out the possible values of x and their y values associated. So the possible values of x go from 1 to 2 by 1/4. In this case, we're taking left endpoints, so we take the height of the first rectangle, which is x equals 1, because that's the leftmost. Then we increment by 1/4 until we get to 4 rectangles. So these 4 arrows represent the 4 heights of the rectangle that we'll take. So we need the area of each rectangle. The area of each rectangle is base times height, and you add everything up to estimate the total area. So that's why there's a summation here. We can factor out the width because they're the same for each rectangle, but the heights are different. Using the y values, this is what we'll get. And if we simplify that, we have this. Using technology, we can get a better estimation, and we can see that our approximation is actually an overestimate. Now let's estimate the area under the curve, sine x, from 0 to pi over 2 using 4 rectangles and right endpoints. Approximation via right endpoints follows almost the exact same procedure as left endpoints do, but with slight modification. We again start by drawing a picture and getting delta x. In this case, delta x is pi over 8. But since we're using right endpoints, we'll take the rightmost rectangle, or height, which is x equals pi over 8, and then take 4 rectangles from there. The equation is the same. To find the area, you add up all the areas of the rectangles. Each of them have the same width, so you can factor that out. Using the table, this is what we get. We can compare our answer again to technology, which is 1 evenly. And we can see that, again, it's an overestimate. Let's now use midpoint rule to approximate the integral from 0 to 1 of the cube root of x cubed plus 1 using 5 rectangles. We still want to draw a picture, and we still want to find delta x. The procedure doesn't change, but we can write the integral in this format because it's the standard way of writing it, and what you'll see for the most part in the future. In this case, though, to get the different heights, we need to take the midpoint of every increment of delta x. So the first increment is from 0 to 1/5. So what is the midpoint between 0 and 1/5? The rule is always add up the endpoints and divide by 2. Remember, delta x is 1/5, so the next increment will be 1/5 to 2/5. The next, 3/5 to 4/5, and so on, until you get to 5/5, 1. Therefore, the second midpoint is between 1/5 and 2/5, so add those up and divide by 2, you'll get the second midpoint. Remember, the midpoints are the heights, and if you repeat this algorithm, you'll get this table. Now you want to plug that into the area formula. And you're going to get this using the table, which simplifies to this, and finally that. Again, using technology, we can see that this is an underestimate, but a much more accurate estimate than left and right endpoints. Let's now transition into the definition of the integral. We use the definition of the integral to find the exact area under the curve, so no approximating. Like many definitions, we hardly ever use it to solve problems in practice. However, it is important to practice using it, especially when learning the new concept in the beginning, so that we can really understand the premise or premises of the mathematical principles involved. So let's give the definition. And we're actually going to need a few summations that will help us calculate the exact area under the curve. The important thing in the definition is delta x and x sub I. Delta x is very familiar. We've been calculating that. And we'll start learning how to calculate x sub I, which comes naturally. The second is that we're essentially taking an infinite number of rectangles as opposed to 4 or 5 rectangles as before. And since we're working with sums, again, we'll be using these 3 summations to help us calculate. Using the definition of the antiderivative, let's evaluate the following integral. To do this, the theorem essentially says that we take an infinite number of n rectangles, and the widths are delta x, and the heights are f of x sub I. Much like the approximations we discussed earlier, every rectangle has the same width but different heights. Each height is represented by f of x sub I. X sub I itself is the ith increment of delta x. So we're essentially following pretty much the same procedure as before, just taking an infinite number of rectangles. So first thing to do like before, find delta x. A and b in this case are 0 and 1. Delta x would be 1 over n. X sub I is the lower bound plus I times delta x. 0 plus I times 1 over n in this case. So we get 1 over ni. Together, we can apply this to the formula given by the theorem, which is this. And remember, this is just the area of a rectangle. And we're taking an infinite number of n rectangles and finding those areas. So plug those 2 things in that you just found, and this is what you get. The reason we write it like this is because this now allows us to compute the answer. This is the form of our answer. 1 over n on the outside comes from taking out delta x. So delta x can be multiplied on the outside. Now, we have to figure out what exactly is f of 1 over ni. Anytime you have f of something, it implies that whatever's in the parentheses, you have to plug into your function f. Our function f is 4 plus 3x squared in this case. So we're plugging 1 over ni into 4 plus 3x squared. So plug 1 over ni into every single x value, and this is what you'll get. Now, that gets replaced, 4 plus 3 times 1 over n squared I squared gets replaced inside the summation. And this is what we have. Anytime you have addition or subtraction within your summation, it's great because you can actually split it up over that. So that's a property of summation. Split it up like this, so you have 2 summations. The first summation actually converges to 4 times n. 1 over n times 4 times n. The second summation is a little bit more difficult though. This is where we have to use one of the 3 equations. So we're going to focus on the second summation here. First, take out 3 over n squared. Take out everything that doesn't depend on I. Everything that doesn't have an I, you take out. So we're going to start simplifying that second summation there using the equation number 6 written on screen. So that gets substituted into the summation. it's what the summation converges to, so the entire summation gets substituted. Now, you have to notice some properties about multiplication. There's n cubed on the bottom, and then n times n plus 1 times 2n plus 1. So essentially, those three n's divide everything that's being multiplied on the top. This simplifies. And then when you let the limit approach, you'll get this. Let's now use the same procedure to solve the second example. You still first want to get delta x and x sub I. Delta x would be 3 over n. X sub I, remember, is the lower bound a plus I times delta x. So 1 plus I times 3 over n in this case. Then you want to plug both of these into the area formula, which is this. When you plug both of them into that formula, or summation, you get this. Eventually, you can do the same thing as before, where you can factor out 3 over n, because the summation does not depend on n. But first, you need to evaluate f of x sub I, which is 1 plus 3ni. Meaning you need to plug in 1 plus 3ni into every single x value that you see. So you're cubing it first, subtracting by 4, then plugging that into the x value and adding 1. To cube it here, you can either use Pascal's triangle to simplify it into the equation, or you can do it the longer way, which is what we'll do, and square it and then multiply it by itself for the first term. So for that first term, I squared it. That's how I get 1 plus 6 over ni plus 9 over n squared I squared. And then you have to multiply it by itself because of the cubed. Then you can distribute the negative 4. From here, you need to do the arithmetic of expanding the first two terms. Once you do that arithmetic, you can also simplify negative 4 plus 1. So that's how I get the negative 3 on the tail end. Now you can simplify some more. And the last step of simplification, where you're combining all the like terms, is this. Now, we're ready to solve the summation because this is what f of 1 plus 3ni is actually evaluated at. So how we're going to do it is we're going to split it up into 4 different summations. And since I cubed is the highest term, I'm going to write that one first. So this is the first summation. Remember, everything is multiplied times 3 over n. Then you add the second summation, which is 27 over n squared I squared. Then the next one would be minus 3ni. And the last one will be minus 2. Remember, the 3n is what we took out in the beginning. That's why it's there for every single one of the 4 terms. Now, you want to simplify. In this case, we're beginning to factor out the n's from the inside of the summations. And also, we are evaluating the summation using the equations 5, 6, and 7. So that first summation, you have I cubed in the inside of the summation, and then you have 81 over n to the power 4 on the outside. Then for the second part, you factor out the 27 over n squared. That's how you get 81 over n cubed. And then I squared is just number 6. And then you're going to subtract and then add. From here, you're going to use the same rule where the number of n's on the denominator cancel out with the number of n's on the numerator of each of these 4 summations. Once you do that, you'll be left with 174 over 4. Thank you for watching another edition of TutorTube. I hope this video helped. Please check out part 2 of the Introduction to Integration, listed in the description below. It will cover U substitution, FTC, and some other integral problems. Make sure to check out our other videos listed in the description as well, and follow us on social media. See you next time.